stars mean that direct stellar collisions are unlikely. Instead, the merger will create tidal tails, intricate streams of stars, and a dramatic reshuffling of galactic components. Andromeda has been studied extensively using both ground-based and space-based telescopes. The Hubble Space Telescope has provided breathtaking images of the galaxy, revealing its intricate spiral structure, star-forming regions, and even individual stars. Future observatories, such as the James Webb Space Telescope and the Extremely Large Telescope, promise to deepen our understanding of Andromeda by studying its stars, planets, and black hole in unprecedented detail. One of the most exciting areas of research involves the search for exoplanets in Andromeda. While detecting planets in another galaxy is extraordinarily challenging, advancements in microlensing techniques and spectroscopy may one day allow us to identify worlds orbiting stars in this neighboring galaxy. Such discoveries could revolutionize our understanding of planetary systems and the potential for life beyond the Milky Way. Andromeda's proximity makes it a valuable reference point for studying galaxies throughout the universe. By examining its structure, composition, and dynamics, astronomers can develop models that apply to galaxies billions of light-years away. The study of Andromeda's dark matter halo, for instance, has implications for understanding the mysterious substance that makes up 85% of the universe's mass. The galaxy also serves as a time capsule, preserving evidence of past interactions with other galaxies. Stellar streams, faint trails of stars torn from satellite galaxies, crisscross Andromeda's halo, offering clues about its history of galactic cannibalism. These remnants of past mergers help astronomers reconstruct the timeline of Andromeda's growth, providing a glimpse into the life cycle of galaxies. Beyond its scientific value, the Andromeda Galaxy has captured the human imagination for centuries. Visible to the naked eye as a faint smudge in the night sky, it has inspired countless myths, artworks, and dreams of intergalactic travel. As our technology advances and our understanding of the cosmos deepens, Andromeda remains a symbol of humanity's insatiable curiosity and our quest to comprehend the universe. Whether through the lens of a telescope or the imagination of a dreamer, the Andromeda Galaxy invites us to ponder profound questions about our place in the cosmos. What stories do its stars tell? What secrets lie hidden within its vast expanse? And what future awaits as our two galaxies converge in a cosmic embrace? The Andromeda Galaxy, or Messier 31, stands as one of the most intriguing and vital cosmic neighbors of the Milky Way. Its staggering proximity of 2.5 million light-years allows astronomers to explore its intricate structure with unprecedented clarity, a window into the processes that govern galaxies across the universe. This massive spiral galaxy, over 220,000 light-years in diameter, surpasses our own Milky Way in size and contains an estimated 1 trillion stars. Its colossal mass and dynamic nature make it a perfect laboratory for studying galaxy formation, star evolution, and the mysterious force of dark matter. Andromeda's double nucleus, a feature visible in its central bulge, has perplexed scientists for decades. This peculiar structure hints at a complex history of mergers and interactions with smaller galaxies. At its core lies a supermassive black hole, approximately 140 million times the mass of the Sun. This black hole exerts a gravitational pull that influences the orbits of nearby stars and triggers high-energy phenomena such as X-ray flares. These intense bursts of radiation illuminate the dynamic and sometimes violent processes that occur in galactic cores. Clouds collapse under gravity to form new stars. Bright blue clusters dot these arms, signifying the presence of massive, young stars that shine intensely before exhausting their fuel and ending their lives in spectacular supernovae. These explosions enrich the galaxy with heavy. The spiral arms of this galactic giant are regions of immense activity, where dense molecular elements, driving the chemical evolution necessary for the formation of planets and, potentially, life. The interstellar medium of Andromeda is also rich with hydrogen gas and cosmic dust, creating vibrant nebulae that serve as the birthplaces of new stars. Unlike our Milky Way, which exhibits a more subtle spiral pattern, Andromeda's arms are well defined, giving it the iconic shape often associated with galaxies. These arms are not static. They are shaped and reshaped by the gravitational interactions with Andromeda's satellite galaxies. Observations reveal that Andromeda is surrounded by a swarm of smaller galaxies, some of which are being torn apart by its gravitational pull. These interactions create streams of stars, known as tidal tails, that arc through Andromeda's halo, providing clues about its history of mergers and acquisitions. Andromeda is not only a showcase of stellar life and death, but also a treasure trove of ancient stars. Its halo contains some of the oldest stars known, remnants from the earliest epochs of galactic formation. By studying these ancient stellar populations, scientists can trace the history of Andromeda back billions of years, uncovering the conditions that prevailed when the universe was young. These studies also shed light on the processes that shaped our own galaxy, offering a broader context for the evolution of the cosmos. One of the most captivating aspects of Andromeda is its future collision with the Milky Way. Observations of its motion indicate that it is hurtling toward us at a speed of approximately 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and merge to form a new, larger galaxy. This event, often described as a galactic dance, will dramatically reshape the structure of both galaxies. Stars, gas, and dark matter will be redistributed in a complex interplay of gravitational forces, creating tidal streams and igniting bursts of star formation. Despite the seeming violence of such a merger, the vast distances between individual stars mean that direct collisions between them are unlikely. Instead, the merger will create a new cosmic entity, sometimes referred to as Milkomeda, with an elliptical structure and a new center of mass. The Andromeda Galaxy has been the focus of numerous scientific missions and observations. The Hubble Space Telescope has provided some of the most detailed images of its structure, capturing its spiral arms, central bulge, and outer halo with stunning clarity. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other spiral galaxies in the universe. Advanced instruments, such as the James Webb Space Telescope, promise to unveil even more secrets, allowing astronomers to study the galaxy's individual stars, planetary systems, and even its dark matter halo with unprecedented precision. The search for exoplanets within Andromeda is a burgeoning field of study. While detecting planets in another galaxy is extraordinarily challenging, techniques such as gravitational microlensing offer a glimpse into this possibility. These methods rely on the bending of light caused by the gravitational field of a planet or star, revealing the presence of celestial objects that would otherwise remain hidden. Discovering exoplanets in Andromeda could revolutionize our understanding of planetary formation, potentially revealing worlds vastly different from those in the Milky Way. Andromeda's immense halo of dark matter extends far beyond its visible disk, influencing the motion of its stars and satellite galaxies. This unseen component constitutes the majority of the galaxy's mass, yet its nature remains one of the greatest mysteries in astrophysics. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock the secrets of this enigmatic substance, which plays a crucial role in the formation and evolution of galaxies throughout the universe. As the largest galaxy in our local group, Andromeda serves as a cosmic mirror, reflecting the processes that govern galaxies on larger scales. Its intricate structure, active star-forming regions, and dynamic interactions with other galaxies provide a microcosm of the universe's complexity. By studying Andromeda, astronomers gain insights into phenomena that apply to galaxies billions of light-years away, bridging the gap between our local universe and the distant cosmos. The Andromeda Galaxy is not just an object of scientific inquiry, it is a source of inspiration and wonder. Its visibility to the naked eye as a faint smudge in the night sky has captivated observers for centuries, from ancient astronomers who catalogued it as a nebula to modern scientists who unravel its mysteries with cutting-edge technology. Andromeda represents humanity's enduring quest to understand the cosmos, a testament to our curiosity and imagination. The Andromeda Galaxy is a beacon of cosmic curiosity, continuously drawing the gaze of astronomers and dreamers alike. Its vastness and complexity defy easy understanding, inviting deeper exploration with every new discovery. This galactic giant is not just a collection of stars, gas, and dark matter, it is a storybook of the universe itself, containing chapters that span billions of years and countless transformations. The study of Andromeda has provided humanity with unparalleled insights into the life cycles of galaxies. Its close proximity makes it an ideal target for research, as we can observe its individual stars and clusters with remarkable clarity. Scientists have identified diverse stellar populations within Andromeda, each with unique characteristics and histories. From the bright, young blue stars of its spiral arms to the ancient, red stars in its halo, every stellar population tells a different part of the galaxy's story. These stars are not just cosmic objects, they are timekeepers, offering clues about the conditions that shaped Andromeda over its lifetime. Andromeda's history is written in the light of its stars, but it is also etched in the faint streams of material that surround it. These tidal streams are the remnants of smaller galaxies that were torn apart and absorbed by Andromeda's gravity. By mapping these streams, astronomers can reconstruct the galaxy's dynamic past, piecing together the cosmic interactions that have shaped its structure. Each stream represents a merger, a collision, or a gravitational tug-of-war that occurred millions or even billions of years ago. Together, they form a mosaic of Andromeda's evolutionary journey, providing a glimpse into the violent processes that drive galactic growth. The role of dark matter in Andromeda's formation and evolution cannot be overstated. This invisible, enigmatic substance makes up the majority of the galaxy's mass, yet its true nature remains one of the greatest unsolved mysteries in modern science. Dark matter does not emit or absorb light, making it undetectable through conventional means. However, its presence is inferred from its gravitational effects on visible matter. In Andromeda, dark matter forms an extensive halo that stretches far beyond the galaxy's luminous disk, influencing the motion of its stars and satellite galaxies. By studying the distribution and behavior of dark matter in Andromeda, scientists hope to unlock clues about the fundamental composition of the universe itself. Andromeda's future is as fascinating as its past. The impending collision with the Milky Way is not just an event of local significance, it is a cosmic spectacle that will reshape the local group of galaxies. This merger will occur over billions of years, beginning with subtle gravitational interactions that will distort the shapes of both galaxies. As the two spiral galaxies draw closer, their stars will form tidal bridges, connecting the two systems in a gravitational embrace. Gas clouds will collide, triggering bursts of star formation and creating brilliant nebulae that will light up the night skies of any planets within these galaxies. Eventually, the two galaxies will merge into a single, massive elliptical galaxy, a testament to the transformative power of gravity on cosmic scales. While the prospect of this collision may seem daunting, it is a reminder of the dynamic and ever-changing nature of the universe. Galaxies are not static islands of stars, they are constantly interacting, merging, and evolving. The Andromeda Milky Way collision will not only reshape the structure of these galaxies but also provide a unique opportunity to study the processes that drive galactic evolution. For astronomers billions of years in the future, this event will be a natural laboratory for understanding the interplay of gravity, dark matter, and interstellar gas. The Andromeda Galaxy has also inspired humanity to think beyond our own cosmic neighborhood. The possibility of life in Andromeda, while purely speculative, raises profound questions about the nature of the universe and our place within it. If planets orbit stars in Andromeda, and there is no reason to believe they do not, then the potential for life beyond the Milky Way becomes a tantalizing prospect. While the vast distances between galaxies make direct exploration unlikely for the foreseeable future, the study of Andromeda fuels our imagination and drives the development of new technologies that may one day bring us closer to answering these profound questions. Telescopes have played a crucial role in our understanding of Andromeda, transforming it from a faint smudge in the night sky to one of the most studied objects in the universe. Ground-based observatories equipped with advanced adaptive optics systems have provided detailed views of the galaxy's structure, while space-based telescopes like Hubble have captured breathtaking images that reveal its intricate beauty. These observations have not only deepened our understanding of Andromeda but also served as a benchmark for studying other galaxies. By comparing Andromeda to galaxies at various distances, astronomers can piece together a timeline of cosmic history, tracing the evolution of galaxies from the early universe to the present day. Andromeda's spiral arms, central bulge, and halo are all areas of active research, each offering unique insights into the workings of galaxies. The spiral arms are regions of intense star formation, where massive stars light up the surrounding gas and dust, creating some of the most beautiful and dynamic regions in the galaxy. The central bulge, by contrast, is dominated by older stars, providing a window into the galaxy's past. The halo, with its sparse population of ancient stars and globular clusters, represents the remnants of Andromeda's earliest epochs, a fossil record of the galaxy's formation and growth. As we continue to study Andromeda, we are reminded of the interconnectedness of all things in the universe. The same processes that shape this distant galaxy are at work in the Milky Way and countless other galaxies. By studying Andromeda, we gain a deeper understanding of our own galaxy, our place in the cosmos, and the forces that govern the universe. The Andromeda Galaxy stands as a pillar of scientific curiosity and inquiry, revealing profound truths about the universe's structure and evolution. Each observation, each analysis of this celestial neighbor deepens our understanding of the intricate forces that shape galaxies, including our own Milky Way. Scientists and astronomers have spent decades unraveling its mysteries, from its unique physical characteristics to the secrets hidden in its dark matter halo, which stretches far beyond its visible edges. To expand the horizon of understanding Andromeda, we delve even deeper into the vast scientific details that define this monumental galaxy. One of the key features of Andromeda is its massive dark matter halo, a structure so vast and diffuse that it dominates the dynamics of the galaxy. Observations suggest that this halo extends hundreds of thousands of light-years beyond the galaxy's luminous disk, encompassing both its satellite galaxies and intergalactic space. Unlike the stars and gas within the galaxy, dark matter does not interact with electromagnetic forces, making it invisible to telescopes. However, its gravitational effects are profound. The motion of stars in Andromeda's outer regions can only be explained if we account for the gravitational influence of this unseen mass. The study of Andromeda's dark matter halo has significant implications for cosmology. By measuring its distribution and density, astronomers can test theories about the formation of large-scale structures in the universe. The presence of such a massive halo supports the lambda-CDM, lambda-cold dark matter, model, which posits that galaxies form within vast, invisible scaffolds of dark matter. Furthermore, detailed mapping of Andromeda's halo through gravitational lensing and stellar dynamics provides clues about the nature of dark matter particles, one of the most elusive questions in modern physics. Another remarkable aspect of Andromeda is its double nucleus, a feature that has fascinated scientists since its discovery. This central region contains two distinct clusters of stars, separated by only a few light-years. The prevailing hypothesis is that one of these clusters represents a dense group of stars surrounding Andromeda's supermassive black hole, while the other is a remnant of a smaller galaxy that merged with Andromeda long ago. This unusual configuration offers a unique opportunity to study the dynamics of galactic nuclei and the behavior of stars in extreme gravitational environments. The supermassive black hole at the center of Andromeda is estimated to be about 140 million times the mass of the Sun, significantly larger than the black hole at the center of the Milky Way. This immense gravitational powerhouse shapes the orbits of stars within the galaxy's central bulge and influences the flow of interstellar gas. Observing the interactions between this black hole and its surroundings provides critical data for understanding the growth and evolution of supermassive black holes across the universe. These observations also help astronomers explore the relationship between black holes and their host galaxies, a fundamental question in astrophysics. Andromeda's satellite galaxies add another layer of complexity to its story. These smaller galaxies, such as M32 and M110, orbit Andromeda in intricate patterns, influenced by its massive gravitational pull. Some of these satellites are in the process of being torn apart, their stars and gas streams forming tidal tails that arc across the sky. These interactions offer a glimpse into the hierarchical nature of galaxy formation, where larger systems grow by accreting smaller ones. By studying these satellites and their interactions with Andromeda, scientists can reconstruct the galaxy's merger history, tracing its growth over billions of years. The star-forming regions within Andromeda are particularly noteworthy for their scientific importance. These areas, known as HII regions, are dense clouds of ionized hydrogen where new stars are born. Observations of these regions provide valuable insights into the processes that govern star formation, such as the role of magnetic fields, turbulence, and feedback from massive stars. The distribution and intensity of star-forming regions within Andromeda's spiral arms also shed light on the dynamics of spiral galaxies, revealing how density waves and gravitational interactions shape their structure. Andromeda's globular clusters, ancient spherical collections of stars, are another key area of research. These clusters, which orbit the galaxy in its halo, are among the oldest objects in the universe, with ages exceeding 10 billion years. By studying the chemical composition and motion of these clusters, astronomers can infer the conditions that prevailed in the early universe when Andromeda was forming. Some globular clusters in Andromeda are thought to have originated in smaller galaxies that were later absorbed by the larger system, providing further evidence of its dynamic and turbulent history. One of the most exciting fields of research involving Andromeda is the search for exoplanets within its borders. While detecting planets in another galaxy is extraordinarily challenging, advancements in observational techniques have made this possibility increasingly feasible. For example, gravitational microlensing, a phenomenon where a massive object bends and magnifies the light of a more distant star, can be used to detect planets in Andromeda. If successful, these efforts could reveal the first evidence of planetary systems beyond the Milky Way, offering a new frontier for the study of exoplanets and the potential for life elsewhere in the universe. The impending collision between Andromeda and the Milky Way is one of the most significant events in the galaxy's future. As the two galaxies approach each other, their gravitational interactions will initiate a complex series of events that will reshape both systems. Gas clouds will collide, triggering bursts of star formation that will light up the night sky. Spiral arms will be torn apart, forming tidal streams and bridges of stars. Over billions of years, the two galaxies will merge into a single, massive elliptical galaxy. Simulations of this process provide a detailed look at how such mergers unfold, offering a unique perspective on the long-term evolution of galaxies. The study of Andromeda extends beyond the visible spectrum. Observations in infrared, ultraviolet, and X-ray wavelengths have revealed phenomena that are invisible to the human eye. Infrared studies, for example, penetrate the dust clouds within Andromeda, uncovering regions of intense star formation and the distribution of cooler stars. Ultraviolet observations highlight the youngest and hottest stars, while X-ray studies detect high-energy processes near the galaxy's supermassive black hole and in its dynamic star-forming regions. Together, these observations provide a multi-wavelength view of Andromeda, allowing astronomers to build a comprehensive picture of its structure and activity. Andromeda continues to inspire not only scientists but also the broader public, serving as a symbol of humanity's quest to explore and understand the universe. Its presence in the night sky, visible as a faint smudge to the naked eye, connects us to the vastness of the cosmos and reminds us of our place within it. Through telescopes and spacecraft, we have transformed this distant neighbor from an object of curiosity into a cornerstone of modern astrophysics, a testament to the power of human ingenuity and imagination. The Andromeda Galaxy is more than just a spiral of stars, gas, and dust. It is a dynamic system governed by complex physical processes that stretch the boundaries of our understanding. Each layer of Andromeda, from its luminous core to its diffuse halo, offers a wealth of information about the forces shaping galaxies, the origins of the universe, and the interconnected nature of cosmic structures. To truly appreciate the depth of Andromeda's scientific significance, we must dive further into its intricate details, probing the mechanisms that govern its past, present, and future. One of the most intriguing phenomena in Andromeda is the ongoing interaction between its stars and interstellar medium, ISM. The ISM is a mixture of gas, dust, and plasma that permeates the galaxy, acting as the raw material for star formation. Andromeda's ISM is highly structured, forming filamentary clouds, dense clumps, and expansive regions of ionized gas. Observations of the ISM reveal the complex interplay between gravity, magnetic fields, and feedback from stellar winds and supernovae. These processes regulate the galaxy's star formation rate, determining how efficiently Andromeda converts gas into stars over time. Star formation within Andromeda is not uniform, it is concentrated in specific regions, particularly along the spiral arms. These arms are sites of enhanced density, where shock waves from density waves compress gas clouds, triggering gravitational collapse. The role of density waves in spiral galaxies like Andromeda has been a subject of extensive study, as they provide a framework for understanding the long-lived spiral patterns observed in galaxies. These waves are essentially gravitational oscillations that propagate through the disk of the galaxy, concentrating stars and gas into spiral patterns without the material itself permanently remaining in the arms. This dynamic structure ensures a steady cycle of star formation and dispersal. The star formation process itself is driven by a delicate balance of forces. Gravity works to collapse gas clouds, forming protostars, while thermal pressure, turbulence, and magnetic fields resist collapse. In Andromeda, regions of active star formation are often accompanied by intense feedback from massive stars. These stars emit powerful ultraviolet radiation, which ionizes the surrounding gas, creating glowing nebulae known as HII regions. As these stars reach the end of their lives, they explode as supernovae, releasing vast amounts of energy and enriching the ISM with heavy elements. This enrichment is a critical step in the chemical evolution of galaxies, as it provides the building blocks for planets and life. The chemical composition of Andromeda's stars and ISM offers insights into its history of star formation and mergers. Spectroscopic studies reveal a gradient in metallicity, the abundance of elements heavier than hydrogen and helium, across the galaxy. The central bulge, which contains older stars, has a higher metallicity, reflecting a history of intense star formation in the galaxy's early years. In contrast, the outer regions of the disk and halo have lower metallicity, suggesting a slower rate of chemical enrichment. This gradient is a fingerprint of the processes that have shaped Andromeda over billions of years, from its initial collapse to its interactions with other galaxies. Andromeda's globular clusters are another rich source of information about its chemical and dynamical history. These dense collections of stars are among the oldest objects in the galaxy, with ages often exceeding 10 billion years. By studying the motions and compositions of these clusters, astronomers can reconstruct the conditions that prevailed when Andromeda was forming. Some globular clusters exhibit unusual properties, such as retrograde orbits or distinct chemical signatures, suggesting that they originated in smaller galaxies that were later accreted by Andromeda. These findings support the hierarchical model of galaxy formation, in which large galaxies grow through the assimilation of smaller systems. Beyond its visible components, Andromeda's structure is profoundly influenced by its dark matter halo. This halo, which extends far beyond the galaxy's disk, dominates its mass and shapes the motion of stars and satellite galaxies. By measuring the rotation curve of Andromeda, how the orbital speed of stars varies with distance from the center, astronomers have inferred the presence and distribution of dark matter. The flatness of the rotation curve at large distances, where visible matter becomes sparse, is a clear indication of the gravitational influence of dark matter. This discovery has been pivotal in the development of modern cosmology, highlighting the importance of unseen components in shaping the universe. The relationship between Andromeda and its satellite galaxies is another area of intense study. These smaller systems, such as M32, M110, and others, are bound to Andromeda by its gravitational pull, forming a miniature ecosystem within the local group. Some of these satellites are in the process of being disrupted, their stars forming tidal streams that weave through Andromeda's halo. These streams provide a snapshot of galactic cannibalism in action, illustrating how large galaxies grow by accreting smaller ones. By mapping these streams, astronomers can reconstruct the orbits of the disrupted galaxies, revealing the history of their interactions with Andromeda. The study of Andromeda extends beyond its stars and dark matter to its population of supermassive black holes, neutron stars, and other exotic objects. The central black hole, with a mass of 140 million suns, is a key feature of the galaxy's core. This black hole influences the orbits of nearby stars and may play a role in regulating the flow of gas into the central regions. Observations of X-ray and radio emissions from the core provide clues about the activity of this black hole, which is currently in a relatively quiescent state. Future observations may reveal periods of increased activity, such as flares caused by the accretion of matter. Andromeda's neutron stars and stellar mass black holes are remnants of massive stars that have completed their life cycles. These objects are often found in binary systems, where they accrete matter from a companion star. As this matter falls onto the compact object, it releases energy in the form of X-rays, creating some of the brightest sources in the galaxy. Studying these systems in Andromeda provides insights into the end stages of stellar evolution and the dynamics of binary systems. The future of Andromeda is perhaps its most captivating aspect. Its collision with the Milky Way will mark a new chapter in the history of both galaxies, reshaping their structures and forming a new cosmic entity. Simulations of this merger reveal the complex interplay of gravitational forces, which will tear apart the spiral arms, create tidal bridges and streams, and trigger bursts of star formation. Over billions of years, the two galaxies will settle into a massive elliptical galaxy, a testament to the dynamic and interconnected nature of the cosmos. As we probe deeper into the Andromeda galaxy, it becomes increasingly clear that this celestial neighbor is not just an isolated system but a microcosm of the universe. Its intricate structure, dynamic interactions, and rich history make it a cornerstone of modern astrophysics, offering answers to some of the most profound questions about the nature of galaxies and the forces that govern the cosmos. The Andromeda Galaxy, our closest galactic neighbor, is not just a vast collection of stars, gas, and dark matter, it's a living laboratory where the secrets of the universe are constantly unfolding. Every corner of this colossal spiral galaxy, from its glittering core to its faint outer halo, holds stories of creation, destruction, and rebirth on a scale that challenges the limits of human imagination. At the heart of Andromeda's mysteries lies a component we cannot see, dark matter. This enigmatic substance, which makes up most of the galaxy's mass, doesn't emit light, heat, or any detectable radiation. Instead, we infer its presence through its gravitational influence on the galaxy's stars and gas. Without dark matter, Andromeda's majestic spiral arms wouldn't hold together, they would have unraveled long ago. Dark matter forms a vast, invisible halo around Andromeda, extending hundreds of thousands of light-years beyond its visible disk. The gravity of this halo acts as scaffolding, pulling stars, gas, and dust into the familiar spiral structure we observe today. Mapping this halo is one of the most exciting challenges in astrophysics. Using gravitational lensing, a phenomenon where dark matter bends the light of background objects, astronomers are beginning to trace its contours, revealing a hidden architecture that underpins the galaxy. This work isn't just about understanding Andromeda. Dark matter halos like this exist around all galaxies, and by studying the closest example, we gain insight into the invisible framework that shaped the entire universe. Andromeda's core is unlike anything in the Milky Way. At its center lies not one, but two dense clusters of stars, a double nucleus. One cluster orbits a supermassive black hole that's 140 million times the mass of the Sun. The other, offset slightly, might be the remnants of a smaller galaxy swallowed by Andromeda in the distant past. Why does Andromeda have two nuclei? One hypothesis is that the second cluster is the ghost of a galactic collision. Billions of years ago, Andromeda likely devoured a smaller galaxy, and its core didn't disintegrate entirely, it became trapped, orbiting within Andromeda's gravitational well. Over time, the orbits of these two clusters will likely merge, adding to the already extraordinary mass of the central black hole. Andromeda's spiral arms are bustling regions of activity where stars are born. These arms are shaped by waves of density, essentially gravitational traffic jams. As gas clouds enter these high-density regions, they slow down, compress, and ignite in bursts of star formation. Massive blue stars, some tens of times the mass of the Sun, dominate these regions, shining brightly but living short, fiery lives before exploding as supernovae. These explosions are cosmic recycling events. They scatter heavy elements, like carbon, oxygen, and iron, into the surrounding space, enriching the galaxy's interstellar medium. Without these elements, planets like Earth and life as we know it couldn't exist. In a way, Andromeda's star-forming regions are factories producing the raw materials for future worlds. Beyond its bright core and spiral arms lies Andromeda's halo, a dim, extended region filled with ancient stars and faint remnants of past collisions. This halo is a treasure trove for galactic archaeologists, astronomers who reconstruct the history of galaxies by studying their structures and stellar populations. One of the most fascinating features in Andromeda's halo is its stellar streams, long, faint trails of stars left behind by smaller galaxies that Andromeda has absorbed over billions of years. These streams are cosmic fossils, preserving the memory of galactic mergers. By mapping these trails, astronomers can recreate Andromeda's growth history, revealing a violent past of collisions and cannibalism. The largest and most famous of these streams is the giant stellar stream, a 100,000 light-year-long ribbon of stars thought to be the remains of a once massive satellite galaxy. Studying these structures helps scientists understand not just Andromeda's history, but also how galaxies like the Milky Way grow through mergers and accretion. Perhaps the most dramatic chapter in Andromeda's story is yet to come. Observations show that Andromeda is hurtling toward the Milky Way at a speed of 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide in a cosmic event that will reshape the local group of galaxies forever. What will happen during this collision? As the galaxies approach, their gravitational forces will pull at each other, distorting their shapes and flinging stars into long tidal tails. Gas clouds will collide, sparking bursts of star formation on an unprecedented scale. Over time, the two galaxies will merge into a single, massive elliptical galaxy, often nicknamed Milkomeda. Despite the scale of this event, individual stars are unlikely to collide due to the vast distances between them. Instead, The collision will create a spectacular light show, with new stars igniting and tidal streams painting the night sky. Andromeda's stars likely host countless planets, yet we've only just begun to explore this possibility. Detecting planets in another galaxy is an extraordinary challenge, but emerging techniques like gravitational microlensing are opening new doors. Microlensing occurs when a massive object passes in front of a background star, magnifying its light and revealing the presence of orbiting planets. If planets are found in Andromeda, they could be vastly different from those in the Milky Way, shaped by the unique environment of their galaxy. Some might orbit stars in dense clusters, experiencing a sky filled with thousands of brilliant suns. Others might lie in regions of relative isolation, circling stars on the edges of the galaxy's spiral arms. The discovery of exoplanets in Andromeda would not only expand our understanding of planetary systems but also ignite the imagination, reminding us of the potential for life beyond our galactic borders. The Andromeda Galaxy is more than a cosmic neighbor, it is a gateway to understanding the universe itself. Its proximity allows us to study phenomena that occur in distant galaxies but are too faint to observe in detail. By examining Andromeda's structure, star populations, and interactions, we gain a clearer picture of how galaxies form, evolve, and eventually meet their fate. Andromeda is a living reminder of the interconnectedness of the cosmos. Its stars, much like those in our Milky Way, are born, live, and die in cycles that produce the elements necessary for life. Its dark matter halo, mysterious and invisible, binds it together, just as dark matter structures the universe on the largest scales. As we look toward Andromeda with ever-advancing telescopes and instruments, we are not just observing another galaxy, we are peering into the mechanisms that govern the cosmos itself. And in its vastness, we are reminded of our small but significant place in this grand, unfolding story. The Andromeda Galaxy is a testament to the universe's complexity, a place where science converges with the unknown. Every new observation of its vast expanse reveals another piece of the puzzle about galactic evolution and the forces shaping the cosmos. The galaxy's massive disk contains over 1 trillion stars, a stellar population far larger than that of the Milky Way. Within this stellar population, we find stars in every stage of their life cycle, from bright, young blue stars to ancient red giants that serve as time capsules from an earlier universe. This mixture of stars offers a unique opportunity to study how galaxies grow and change over billions of years. The interplay between stars and their surrounding environment is evident in Andromeda's disk. Its regions of active star formation are lit up by massive, short-lived stars whose intense ultraviolet radiation ionizes nearby gas clouds, creating glowing nebulae. These regions are dynamic, constantly reshaped by the forces of stellar winds and supernova explosions. Such activity enriches the interstellar medium with heavier elements, providing the raw materials for the next generation of stars and planets. Beyond its spiral arms lies a much fainter halo of stars, globular clusters, and streams of debris from past galactic interactions. This halo, extending hundreds of thousands of light-years from the galaxy's center, is a goldmine for understanding Andromeda's violent history. Stellar streams, such as the giant stellar stream, are remnants of smaller galaxies that Andromeda absorbed, a process that continues to this day. These streams are faint and difficult to detect, but their existence provides critical evidence of the hierarchical nature of galaxy formation, where larger systems grow through the accretion of smaller ones. At the core of Andromeda lies its supermassive black hole, surrounded by a dense swarm of stars. This black hole, millions of times the mass of the Sun, is a region of intense gravitational forces. Stars in the vicinity of the black hole exhibit rapid orbital motions, a direct consequence of its immense mass. While currently in a relatively dormant state, this black hole has likely experienced periods of heightened activity, consuming nearby material and releasing enormous amounts of energy. Observing these central regions offers a glimpse into the processes that occur in galactic nuclei, phenomena that are common throughout the universe but challenging to observe in distant galaxies. Andromeda's double nucleus adds another layer of intrigue to its central region. This dual structure, consisting of two closely separated clusters of stars, suggests a complex history of mergers and interactions. One hypothesis is that this feature represents the remnants of a smaller galaxy's core, trapped in Andromeda's gravitational field after a past collision. Such findings illustrate the dynamic and ever-changing nature of galaxies, where interactions with neighbors leave lasting imprints on their structure. As we move outward from the core, the galaxy's spiral arms showcase the intricate patterns formed by density waves. These arms are not static structures but rather regions of increased density that rotate with the galaxy, compressing gas clouds and triggering star formation as they move. The arms' composition, a mix of bright young stars and dark interstellar dust, highlights the ongoing processes that sustain the galaxy's activity. Andromeda's relationship with its satellite galaxies further enriches its story. These smaller companions, such as M32 and M110, orbit within its gravitational influence, and some are being actively disrupted. Tidal forces exerted by Andromeda pull stars and gas from these satellites, adding to the galaxy's mass and leaving behind streams of debris. Observing these interactions helps astronomers understand how galaxies grow over time and how smaller systems contribute to the evolution of larger ones. The dark matter halo surrounding Andromeda is a dominant feature of its structure, extending far beyond its visible components. This halo, made of unseen material, accounts for the majority of the galaxy's mass. Its gravitational influence shapes the orbits of stars and satellite galaxies and plays a crucial role in maintaining the stability of the spiral arms. Mapping the distribution of dark matter in Andromeda provides a critical test for theories about the nature of this mysterious substance and its role in the formation of large-scale cosmic structures. Andromeda's impending collision with the Milky Way is one of the most dramatic events in its future. As the two galaxies approach each other, their mutual gravitational pull will distort their shapes, creating tidal tails and bridges of stars. Gas clouds from both galaxies will collide, igniting bursts of star formation that will illuminate the night skies. Over billions of years, the two systems will merge, forming a massive elliptical galaxy. While such an event might seem catastrophic, the vast distances between individual stars mean that direct collisions are unlikely. Instead, the merger will result in a profound reshaping of both galaxies, a process that has occurred countless times throughout the universe's history. The study of Andromeda extends beyond visible light, with observations across the electromagnetic spectrum providing a more complete picture of its structure and activity. Infrared observations penetrate the dust in its spiral arms, revealing regions of active star formation. Ultraviolet light highlights young, massive stars, while X-ray emissions point to high-energy processes near the supermassive black hole and within binary star systems. Each wavelength reveals a different aspect of the galaxy, contributing to a comprehensive understanding of its nature. Andromeda's role in the local group of galaxies extends beyond its interactions with the Milky Way and its satellites. As the largest galaxy in this group, it exerts a significant gravitational influence, shaping the motions of neighboring galaxies. These interactions provide a scaled-down model of the processes that occur in larger galaxy clusters, where gravitational forces and mergers dominate the dynamics of the system. Studying Andromeda also offers a window into the conditions necessary for the formation of habitable planets and the potential for life beyond the Milky Way. While direct detection of exoplanets in Andromeda is not yet possible, the principles of planetary formation suggest that its stars likely host a diverse array of planets. If life exists elsewhere in the universe, studying nearby galaxies like Andromeda helps us understand the environments where it might thrive. The Andromeda Galaxy, in its immense complexity and dynamic nature, stands as a microcosm of the universe itself. Its stars, gas, dark matter, and interactions with neighboring systems embody the forces that shape galaxies on all scales. As technology advances, our ability to study Andromeda will only deepen, offering new insights into the workings of the cosmos and our place within it. Each discovery within Andromeda's borders reminds us of the intricate and interconnected nature of the universe, a tapestry woven from countless interactions over billions of years. The Andromeda Galaxy's complexity extends into every observable component, providing endless avenues for scientific discovery. Its stars, spanning a wide range of ages and compositions, form the backbone of its luminous structure. By examining the light emitted by these stars, astronomers have gained a detailed understanding of their chemical abundances, ages, and distribution throughout the galaxy. These stellar populations are grouped into distinct categories: the young, massive stars in the spiral arms, the older, metal-rich stars in the bulge, and the ancient, metal-poor stars in the halo. Each group tells a different chapter of Andromeda's history, revealing how the galaxy grew and evolved over cosmic time. The young stars in Andromeda's disk are concentrated in its spiral arms, where conditions are ideal for star formation. These regions are shaped by density waves, which compress gas clouds as they travel through the disk. This compression triggers gravitational collapse, leading to the birth of new stars. Observing these regions allows scientists to study the initial stages of stellar evolution, from protostars to fully formed stars. The intense radiation from young, massive stars heats the surrounding gas, creating ionized bubbles that emit light across the electromagnetic spectrum. The older stars in Andromeda's bulge, by contrast, are remnants of the galaxy's early history. These stars formed during a period of intense star formation that occurred billions of years ago, likely fueled by the inflow of gas from the early universe. The bulge's stars are densely packed, orbiting the galaxy's center in a complex gravitational dance. Their chemical composition reflects the conditions of the early universe, providing a glimpse into the processes that enriched the interstellar medium with heavy elements. Andromeda's halo contains some of the oldest stars in the galaxy, as well as a population of globular clusters that date back to its formation. These clusters, which contain hundreds of thousands of stars, are relics of the early universe, surviving relatively unchanged over billions of years. The motion and composition of these clusters offer clues about Andromeda's formation, suggesting that many of them originated in smaller galaxies that were later absorbed. Studying these ancient structures helps scientists understand the earliest stages of galaxy formation, a process that began less than a billion years after the Big Bang. The halo is also home to Andromeda's faintest and most elusive components, its stellar streams. These streams are the remnants of smaller galaxies that Andromeda captured and disrupted through gravitational interactions. By mapping the distribution of these streams, astronomers can reconstruct the galaxy's merger history, revealing a timeline of interactions that shaped its current structure. These streams are not static, they evolve over time, mixing with Andromeda's halo and contributing to its overall mass. Andromeda's dark matter halo, though invisible, is one of its most significant features. This vast, diffuse structure extends far beyond the visible galaxy, accounting for most of its mass. Without the gravitational pull of dark matter, Andromeda's stars and gas would not remain bound, and its spiral structure would not persist. The presence of dark matter is inferred from the galaxy's rotation curve, which remains flat.